X and Y are independent variables with common MGF. Mt equals e power t squared by 2. Let w is equal to x plus y, z is equal to y minus x. Find the joint MGF of w and z. Now, MGF of a single variable is defined as, so if the variable is x, then m subscript x of t is the notation for the MGF, and that's the expected value of e power tx. The joint MGF of two variables w and z is defined as expected value of e power t1w plus t2z. I mean, sometimes we write subscripts in the for the m. If there's any confusion, like here, we could even omit the subscript if there is no confusion. In this case, they just said m of t because it was the MGF for both x and y. So here it was more because of convenience than anything else. And similarly here, it's okay if you write the w and z in subscript, and even if you don't, that's okay as long as there's no ambiguity. So for this problem, we are given that the MGF of x and y is e power t squared by 2. So what that means is that expectation of e power tx is e power t squared over 2, and also expectation of e power ty is e to the t squared by 2. Both x and y have the same MGF. And this will be used later on. That's why I've numbered this equation. So we want the MT1, T2. So that by definition is this expected value. And now substitute the value of W and Z. W was X plus Y and Z was Y minus X in the given. And now I collect the X terms together. So that'd be T1 minus T2 with the X. And similarly, I collect the Y terms, and that's T1 plus T2 with the Y. And then that's just this one plus this one in the power. So I break it into a product, e power this first thing, and e power times e power the second thing. And the reason why we break this up is that we want to use equation number 1 now. Because in equation number 1, to use that, you should either have expectation of just a x function or expectation of just a y function, and then you get that. So now the first thing here is that we are given that x and y are independent. So x and y are independent. So whenever two variables are independent, then any functions of them are also independent. So e power t1 minus t2 times x is actually a function of x. And similarly, e power t1 plus t2 of y is a function of y. And since x and y were independent, so these two functions of x and y will also be independent. And the advantage of knowing that is that now you can break the expected value of the product into the product of the individual expected values. So basically, this now becomes e power expectation of this first times expectation of the second. And now we use equation number 1. We know that e power tx is e to the t squared by 2. So instead of t here, we have t1 minus t2. So it'd be e power, so the expectation of e power t1 minus t2, x will be t1 minus t2 squared by 2. E power t1 minus t2 squared by 2. So the way to read this is that whatever comes with the x, it's that coefficient squared divided by 2. So here t1 minus t2 comes with the x, so it's that squared divided by 2, and the whole thing is in the power of e. Yeah, and exactly same thing for the other one. And now we combine them back. It's e power this times e power this, so we add them up on a single power. And when you simplify this expression, you will get t1 squared plus t2 squared, because this square opens up as t1 squared minus 2t1 t2 plus t2 squared, and this one opens as t1 squared plus 2t1 t2 plus t2 squared, and they have a common denominator of 2, so you add them and the middle terms cancel out, and you have 2t1 squared plus 2t2 squared, and that's divided by 2, so you get t1 squared plus t2 squared in the end, and that is choice E